Good morning. Welcome to Physics 3B. We're going to start off by looking at Chapter 21. These first three chapters that we look at, 21, 22, 23, are going to be looking at the electric force in nature. So kind of back in Physics 3A, we were looking, well, as an example, we looked at gravitational forces. Well, the electric force is another one of those fundamental forces in nature. And so let's take a look and see what this chapter is all about. Here's a list of all the topics. The electric force does get referred to as Coulomb's law. I'm going to tend to call it the electric force. I think that's a better representation of kind of its importance. So that's a list of topics, but let's go ahead and those are there for reference if you need them. So first of all, let's identify that. You guys have probably seen this in your other science classes where you talk about electric charge can either be positive or negative. It's as if there's two different types of charge or two different possible values of electric charge. Now we can trace these all the way back to protons and electrons. So if we take a look at all if we take a look at what things are made out of, at some point we hit the level of atoms and molecules. If we look inside those atoms and molecules, what we find are protons, electrons, and neutrons. And the protons repel each other, the electrons repel each other, but protons and electrons attract each other. And we can represent this, we can designate this effect in terms of something called the electric force. Now what's kind of interesting here is there's neutrons in there too, and you might think, well, the neutrons aren't going to play any kind of a role here. Neutrons, even though they're electrically neutral, they have magnetic fields. Turns out that protons, electrons, and neutrons all have what we call magnetic interactions, and we'll see in a few chapters that electric and magnetic forces are really the same thing. They're all part of one package, the electric magnetic force in nature. Anyway, for right now, we're just looking at the positive and the negative charges on these, and we'll say that the neutrons are electrically neutral. Although they're made out of charged particles, we call those quarks, it does turn out that the charges cancel out. What we call their electric fields cancel out, but the magnetic fields don't. So all three of these, electrons, protons, and neutrons, do have electric magnetic properties to them. Kind of interesting. So for us right now, again, we just have to think in terms of the protons being positive and the electrons being negative. Now, what does that mean when we charge objects? So this is saying that, objects can be charged just through contact. Sometimes when you walk up to an object, maybe you've been walking across a room on some carpet and you touch the wall or you touch a metal doorknob or something and you get an electric shock. We say, well, that's electrons rearranging themselves. So actually walking along the carpet can transfer electrons into you or out of you. You acquire a little bit of an electric charge, and then when you touch something, those electrons can redistribute themselves. So in most materials, the protons and the neutrons are packed together in nuclei, and they're in most material, most solids, are kind of locked into place. But often what we find is that the electrons in materials have a little bit of mobility to them. Electrons can kind of move from one region to another. And this is typically what is happening when we say that we're charging different kinds of objects. So that's kind of interesting. All right, here's another couple of examples here. Let's say that we've got this ruler. It's been charged negatively, which means it has extra electrons. Most materials around us we think of as being very close to being electrically neutral, meaning that the number of electrons more or less matches the number of protons. If we transfer away some of the electrons, so if we find a way to move electrons out of an object, overall it ends up with a positive charge. So now there are not enough electrons that cancel out all the positive charge on the protons, and that object overall is negative. So here's two rulers. They've both been charged with extra electrons. They're both negative, and they repel each other. The same thing if we take two rulers again. So these have been charged positively. Now, how do we charge these things? Well, there are certain materials. If we take, what is it, like silk transfers electrons, I'm not sure which direction. If you're rubbing these with like silk, or if you're rubbing these with fur or something like this, if you're rubbing this through your hair, depending on the materials, the electrons can get transferred in these different directions. So static electricity is kind of an interesting topic here. If we charge something to be positive, one object to be positive and one to be negative, we end up having an attractive force happening from that. It's tricky. I mean, moving these charges around in materials, there are some kind of tricky examples that go along with that. Let's see. This is telling us that, reminding us that electric charge is conserved. And what that means is if we have a collection of objects and we've identified either it's electrically neutral or it's a little bit negative or a little bit positive, that we can follow the charge. If we've got some negative charge built up in some region, we can't just make it disappear. We can move that negative charge over to a different region, but the total amount of electric charge is conserved, and that really comes down to saying that protons are conserved and electrons are conserved. Protons and electrons are conserved particles in nature. Now, I put a disclaimer over here, conserved mostly. There are reactions where we find that we can turn, for example, protons into neutrons, neutrons into protons, or electrons into what are called neutrinos. We'll talk about that at the end of the semester. We'll be looking at particle physics. There's a chapter on particle physics near the end of the semester, and we'll talk about, and even before we get to that, when we get to radioactive decay, is maybe the first time we'll run into this. We'll see examples of protons turning into neutrons or neutrons into protons and see how those reactions take place. But for the most part, the number of protons, number of electrons are conserved, and that means that the charges will be conserved. And even in those reactions that we're going to look at later in the course, where protons are turning into neutrons, charge is still conserved. So electric charge is a fundamental principle that we work from. We don't know of any exceptions of any types of reactions we run where electric charge is not conserved. We can always account for the charge. Now here is, of course, an incorrect picture of an atom. So here is a nucleus. Now it's been labeled as positive. So that nucleus is going to have, some number of neutrons, some number of protons. This one looks like lithium, right? Maybe. If we're saying each charge represents one proton, then this looks like a lithium atom. So we've got a nucleus with 3 protons and some number of neutrons. Let's see, the stable isotopes have, like lithium-6 and lithium-7 are stable. And then we've got 3 electrons, so it's a neutral atom. Now we could remove one of the electrons. With lithium, one of those electrons is very easy to remove. And then it would be charged. It would be an ion. It wouldn't be a neutral atom, but it would be an atom that's in an ion form. We could add an extra electron in, or we could pull an electron out to change that. So our model here is, first of all, this nucleus is way, way too big. So if we think of the atom as being, kind of blown up and looked at in detail, if we took it so it's the size of a room like this, the nucleus is still going to be a tiny, tiny speck. We're going to have to look closely to even identify where it'd be a little tiny grain of sand at the center of the room. So this is not scaled properly. We want to scale the nucleus way, 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 way down. So what fills up most of the space are the electrons. Now, a lot of times we say atoms and molecules are mostly empty space. That's one approach to thinking about this, but if we think of, I've got something solid here, what is it that's making it solid? It's because the electrons, as you guys are probably aware, they're not following orbits like this. They're going to be probability distributions filling that region. So it's the negative charge of the electron that's kind of spread out in that region. And we can think of the electrons as filling up most of the space, okay, in materials. So not orbits. Don't look at that picture the way that it's drawn. Think of it in terms of a probability distribution. So we want the electric force, by the time we've looked at the electric force and then the magnetic force in nature, the electric and magnetic forces, those are the forces that are holding atoms and molecules together. Or let's be more specific. Those are the forces that are attracting the nuclei to the electrons. And then when we bring atoms and molecules together, those are going to be the forces, the electric and magnetic forces, are going to be the forces that are holding different molecules together. Why is it that atoms come together and stick to form certain patterns, certain molecules in nature? It's because of the electric and magnetic force. Now, there's also nuclear forces inside the nucleus holding the protons and neutrons together, and we'll see that later in the course also. We got a couple chapters on nuclear physics, which is a really interesting topic, and so we'll get a chance to take a look at the nuclear forces then. But for right now, we're looking at what holds the electrons and the nuclei together, and those are the electric and the magnetic forces. Everything going on in the, I'm going to say at the atomic and molecular level. All right, here's a good example, right? This is everybody's favorite molecule. Here is H2O. So here's what are labeled as a couple of hydrogen atoms and an oxygen atom. Now again, I think rather than think of it as atoms attract each other, let's look at the constituents. I've got an oxygen nucleus. There's a hydrogen nucleus here, which is basically a proton. A hydrogen nucleus here. And then there's this distribution of electrons. So the electrons are spread all over. They're probability distributions. They're not just point objects that exist that are following some kind of an orbit, but rather we have to think of them as probability distributions. So you can see that this positive and negative charge is kind of spread throughout the molecule. Again, you've got these positively charged nuclei that are not taking up much space. You can think of those as little tiny, almost point-like positive charges. So we actually do refer to those as point charges, whereas the electrons are spread out. So we've got a lot of electron density here. What this picture is trying to show here is that there's just a lot of interesting stuff going on in the way that molecules combine. Every time we bring different nuclei and their electrons together, every time we form molecules, what happens is the electrons are not going to arrange themselves in a pattern that completely cancels out the charge. Okay, it's very unlikely that the charge is perfectly spread out, and as a result, most molecules have little residual charges associated with them. Electrically, they're neutral, right? So we don't have any net charge acting on these. But what we do have are regions of the molecule that are more positively charged, meaning that the electrons don't go there as often. The electron density is not as high there, not enough to offset the positive charge of these nuclei. Over here we're seeing more electron density. And you're thinking, well, why is that? Or maybe you've taken chemistry classes, which is a good chance. And you've talked about, well, the electrons just prefer certain atoms over, or certain nuclei over others. And we'll see later in our course, when we look at the quantum mechanics of atoms and molecules, we'll get a chance to go in and actually understand and maybe do a few calculations showing why this is happening. So this makes it really interesting because it says that when you take different types of molecules out there, molecules that are, you know, occurring in nature, molecules that we're constructing, that they're going to have these different regions of residual positive and negative charge. And that means that molecules will attract each other. They can form certain patterns where the molecules kind of stick together. Okay, so that's going to be certainly a major topic that we're going to keep talking about here. All right, we tend to take materials and divide them into what we call electrical conductors or electrical insulators. The idea with a conductor is that charges are able to move quite freely through that material. Now, when we think about materials that are electrically, that they're conductors, we're really thinking in terms, for the most part, of electrons. So typically, these are some solid materials here, and typically when we say that the charges are able to flow through these conductors, that means that the electrons are able to move. Okay, if the electrons get pushed, the electrons can move around inside conducting materials. Not so with the insulators. So the idea of an insulator, here's a piece of wood right here, is the way the molecules are constructed, the electrons are locked into certain quantum states. The electrons are not able to move around so freely. The electrons are more or less confined within certain chemical bonds. And so the electrons are locked into place versus a piece of metal where all of the electrons are being kind of shared by all the nuclei, and that allows for electrons to kind of move from one region to another. It's not such a big shift in energy for the electrons to move around. In the example with wood, for example, in those molecules, removing some electrons or moving them to a different location in the wood requires a lot of energy input. Here it's very easy to move the electrons around. Here it's very difficult. And that's, for the most part, how electrical conductors and insulators end up being defined, right? In how mobile are the electrons within that material. Okay, and then there are these kind of ideas of, let's say that we've got a charged object here. So we have an object that's charged. I'm not exactly sure if this is an insulator or conductor, but we're taking something that's positively charged and bringing it close to this material. Now this is an insulator. It's a non-conductor is what they're calling it here. And so this is an insulator, and so is it having an effect? And at first you might think, nah, if it's an insulator, it's not going to move anything around. But that's not true. So when we look at even materials that are insulating, things that are non-conductors, the presence of external charges like this actually polarize the material. It's not that the electrons get up and move long distances, but there's a little bit of a shift. If this thing is positively charged, then all the electrons get pulled a little bit in that direction. And so the electrons are not symmetrically placed. The presence of these positive charges are going to have all the electrons get shifted a little bit within those molecules. Okay, so the molecules can become polarized even in the cases where the electrons are not able to get up and move around freely. Okay, they can shift their positions a little bit. And that changes the properties of that material. All right, let's get in and so kind of at the fundamental foundation of all of this is what we call the electric force. And what, for some reason, traditionally we call this Coulomb's law. Again, I'm going to be calling this the electric force. I think, it's like we wouldn't take the gravitational force and name it after somebody. It's too important, it's too fundamental to nature, it belongs to nature. And so the electric force, for me, falls into that category too. So the electric force, also known as Coulomb's law, works this way. It says if I have two objects, and let's start with what we call point charges. So to keep things simple to start with, let's say I have a fairly concentrated object here and it's charged, and an object over here and it's charged. And to represent charge, we're going to use the symbol Q. No, it wasn't my idea. And you guys are thinking, well, wait, didn't we just do thermodynamics and Q was heat? And so maybe it's too soon, but anyway, we're going to use big Q to represent electric charge. So make that distinction right now. Don't think that this Q has anything to do with thermodynamics. This is the amount of electric charge that this object possesses. And Q2 is the amount of electric charge that that object possesses. And when we take two charged objects and we set them at rest, and they are a distance, okay, this is drawn incorrectly. As you guys probably know from gravity, it's got to be measured center to center. And even the center to center is a little bit of an approximation, but the distance here is r, and the distance is from the center of this object to the center of this object. And yes, you guys will lose points if you draw your diagrams the way the textbook has. Okay, so be really careful with that. You'll just get wrong answers if we don't make sure it's center to center distances. So I apologize, I didn't even notice that when I was going through the slides. So r is a distance, okay. Is r the radius? No, it is not. So we ran into this with the gravitational force, and we're running into it again with the electric force in nature, and that is, we want to measure from center to center. Now, does the amount of force is going to depend on how much charge there is in Q1, how much charge there is in Q2, and what is the distance. Is that the only thing it depends on? And it turns out it doesn't. It turns out in the electric force, which is a little different from what we saw with gravity, that if these charges are moving, if they have a velocity, that has an effect on the force. The force also depends on the velocity. Now, is that everything? No, the force also depends on the acceleration. So the electric force, and we'll see later on the magnetic force also, depends not just on how far away the two charges are, but it depends on what their velocity and what their accelerations are. Now, we're going to look at some examples of velocity dependence in the force. In fact, that's going to be essential for looking at magnetic effects. And then in some later chapters, we'll also spend kind of a chapter looking at the acceleration effect. And what we find is, when charges are accelerating, they radiate energy. And that's how a radio station broadcasting or a cell phone transmission with microwaves is working by accelerating charges. Accelerating charges actually radiates energy away, a bunch of photons that make up either something in the microwave region or something in the radio region. Something in your microwave oven works this way. So that comes from accelerating charges. But for now, we're going to keep things simple, and we are just going to be looking at the charges, imagining they're either at rest or they're moving slowly enough we can treat them as if they're at rest. All right, here it is. Here is the formula. The force acting between those two charges that we saw in the previous slide depends on how much charge there is in charge 1, how much charge there is in charge 2, and it divides through by the distance. R clearly is a symbol that represents distance. So divided by distance squared, and then there is a force constant. And the force constant we're going to call little k. Oh, wait a minute. Back in thermodynamics, little k was Boltzmann's constant, and then before that it was the spring constant. And also in thermodynamics, it was the thermal conductivity. I think we're using little k a bit too often. Anyway, this is also too soon, but once we're into electric forces, little k now, when we see it, is the electric force constant. In fact, what we're going to find is not only is it the electric force constant, it's also the magnetic force constant because they're the same force. We'll see how that plays out. Okay, so Q, electric charge. Okay, not only is that the electric charge, it's also the magnetic charge. So all electric and magnetic forces trace back to how much electric/magnetic charge an object has. Okay. Now you may be thinking magnetic charge is like north-south on a compass. That's not true. But we'll get to that in the magnetic chapters, which it's a few chapters ahead, but we'll get there. Again, we have the electric/magnetic charge. That's going to be represented with Q. R is easy to keep track of because R is the first letter in distance, right? Oh, maybe not. Anyway, little r is distance. And then K is the electric/magnetic force constant. And for now, we don't have to think magnetic. So electric charge, distance, electric force constant. That's the formula. Where have we seen that formula before? Does that look familiar at all? Oh yeah, that formula looks just like the gravitational force that we saw back in chapter 6, way back in 3A. Okay, so let's do a side-by-side comparison here. This is the formula we used for the gravitational force. There was a big G, which was the gravitational force constant. It had a value. It had units. The value on the gravitational force constant was 6.67, 10 to the minus 11, newtons meters squared divided by kilograms squared, and I think last semester we voted that everyone's favorite constant, right, was big G, 6.67, 10 to the minus 11. Now, then we put in the masses of the two objects. We measured center to center distances, not surface to surface, center to center, and that was R. Now for the electric force, the principal property is not how much mass the objects have, it's how much electric charge they have. What's the electric charge of object 1? What's the electric charge of object 2? And then we measure the distance. Now the distance works the very same way, so this is just the center to center distance. And of course, since it's a different force within nature, it's going to have a different force constant. Nobody knows why the force constants have the values they have. Why is gravity this strong, and why is the electric force this strong? But what we know is that they do have these values, and they're measurable. So the force constant for the electric force is 8.99, 10 to the 9th. Now, it's a force constant, so it's got units of newtons. It depends on distance, so it's got meters squared. And then it's got some units that we haven't seen before. The big C here is the unit of coulombs. So, for mass, the units we were working in were kilograms. And now that we're moving on to electric forces, the electric charges are going to be measured in something we call coulombs. And we'll have to talk more about that. We got to get the units figured out and become familiar with how the units are going to work with these electric forces. But getting back to the formulas themselves, oh well look, they look just the same. It's just we have to look at charge and we have a different force constant. Other than that, it just looks like the gravitational force. So what that means is if, during Physics 3A, you guys learned gravitational forces pretty well, then you already have a pretty good idea of how the electric forces work. Now here's a couple of exceptions that we have to think about. Gravity. What direction is that force in? If I have two objects that are exerting gravitational forces on each other, and what we found with gravity is always attractive. And the force is going to be directed right back towards where the other object is located. Okay. Now this is actually just a bit of an approximation. You guys may be aware that the formula we worked with back for gravity in chapter 6 dates back to Isaac Newton. And we have a more detailed, more accurate set of formulas now that Albert Einstein developed back in the early 1900s called general relativity. We tend not to use general relativity because mathematically it's like 100 million times more difficult to work with. And in most everyday kind of situations, Newton's approximate formula works really well. But general relativity tells us that gravitational forces also depend on velocities and accelerations. If objects are in motion, that's going to change the gravitational force a little bit. Same thing with the electric forces that we've talked about. So again, these are starting from objects sitting at rest. How much force is there acting between two objects with mass or two objects that have electric charge? Okay, and that's what we're looking at here in chapter 21. And I don't know if I mentioned this yet, but chapter 21's got a lot of stuff in it. So these first two chapters, 21 and 22, are looking at, well, they're introducing the electric force, which we just did, and then they're going to be looking at examples of using the electric force, and then later on we're going to be talking about what's called the electric field. Now, the way that the material got divided up is chapter 21's got a ton of stuff in it. Chapter 22, not so much. And so we're going to spend more time on chapter 21 and not as much on 22. It's just the way the material got divided up between the two chapters. Just looking ahead. So don't get discouraged with chapter 21 if it feels like it's going on forever, because it's got like two or a chapter and a half worth of material, maybe two chapters in there. So just we're going to get through this. All right, back to the electric force, also known as Coulomb's law. The force line connecting the charge. Oh, we didn't do that. Let me get back to here. I didn't quite finish up with this. So gravity is always attractive. What about the electric force? It could be attractive or repulsive. So that makes the electric force a little more complicated to deal with, or a little more intriguing to think about. So if it's two positive charges, they repel. Two negative charges, they would repel. But if I got one positive and one negative, they attract. Now, how big is the force acting on Q1 compared with the force acting on Q2? Well, what the formula tells us is it's the same amount of force. Both objects experience the same force. Well, what happens if charge 1 is 50 times bigger than charge 2? Doesn't matter. They both still experience the same amount of force. The force acting on object 1, the force acting on object 2 are the same. And at that point you go, oh yeah, that's just how gravity worked. The forces acting on the objects were the same value. I didn't have to write F1 and F2 because the amounts of those forces matched. So, okay, and that's going to come up in some examples. So electric forces can be attractive or repulsive. When we get to magnetic, I know I shouldn't keep saying this, when we get to magnetic forces, we're going to find out the forces for magnetic forces can be sideways, which is a little weird. But for right now, everything just looks the same as it did in gravity with gravitational forces. All right, so let's say, and this is just everything we were talking about. I've got object 1 and object 2. They're both positive. They both experience the same amount of force. Now, this slide is very important because what the textbook does is it very carefully identifies what F12 is compared with F21. The magnitudes, the numerical value of F12 and F21, they're the same. So I tend to ignore the subscripts, whether it's 1,2 or 2,1, it's the same thing. Where I'm going to keep, what is different is the direction. So what they're saying is, well, this direction of the force acting on 1 is opposite of the force acting on object 2, but I can keep track of that in my diagram. So the same convention that we've used all through physics 3A, I'm going to keep using that convention, and that is, I'm going to draw a diagram. And the diagram is going to show what direction those force vectors are in. And once I've got the diagram drawn, the only thing left to determine is how large is the numerical value of F12 or F21, and those are going to be the same thing. So I don't have to carry vector signs all the way through. I can break it up. The diagram keeps track of directions, and the numerical values will match. So here's two repelling positive charges, a couple of repelling negative charges, and then an attractive force between a positive and a negative. And then here's a bit of review of what we already just talked about on our own diagram, and that is that the proportionality constant in the electric force is 8.99 10 to the 9th. Now this is worth going back. Oh, it wasn't so far back. How big is the electric force constant compared with the gravitational force constant? And it's enormously bigger. This is, 9 basically times 10 to the 9th. 10 to the 9th is a big number. That's a billion. 9 billion is the numerical value. For big G, the gravitational force constant, it's 10 to the minus 11. So the force constant for the electric force is 11 plus 20 orders of magnitude, 20 powers of 10 larger than the gravitational force. And this is why we typically talk about the gravitational force as a much weaker force in nature. Now, gravity, on the scale of the cosmos, on the scale of the entire universe, gravity becomes the dominant force, and that's because the masses, well, there's a couple reasons here. Masses get to be really large. So when I get an entire planet, or I get an entire star, or a galaxy, the mass of these objects is enormous. Well, why doesn't the electric force get bigger and bigger and bigger? Because the charges cancel out. What happens in nature is we find that objects we look at, if we look at our planet, it's made out of almost an equal number of electrons and protons. And that means that overall, the entire planet is electrically neutral. And that means that the force that one proton experiences due to all the other electrons and protons mostly cancels out. Where the electric forces become important is if we're able to concentrate some number of protons and electrons, if we're able to charge an object so that it has a significant amount of charge concentrated, then the forces get to be really, really large. We can create electric and magnetic forces that are enormously large. But in most cases, the protons and electron charges just cancel out. Gravity doesn't work that way. If I add more and more protons and electrons together, the mass just keeps going up. So for a planet or a star, gravity, that's the dominant force. But when I'm looking at objects, if I'm just picking up a different everyday familiar object or something, and asking what are the forces holding this together, or what's the forces holding this together, they're electric. So it's the electric and the magnetic forces that are holding the atoms and the molecules together for everyday kind of objects. Kind of interesting, the force constants are so different. Now another thing we should mention here is, well, we have different units also. So these two force constants, they share units of newtons and meters squared. But the smallness of the electric force constant is partially due to the fact that we think of objects in terms of kilograms. We tend to use a fairly small amount of mass. It works out to be something significant to us. And then the coulombs, well, we'll talk more about what coulomb units are. If we change the units, then those force constant numerical values would also change. Okay, so here's the force constant. Now what it says is that everyday kind of charges that we produce, just by, say, rubbing objects together, they tend not to be any bigger than, maybe a millionth of a coulomb. Coulombs were defined in terms of electric circuits. And so if I have an electric circuit, we can have quite a lot of charge moving around in an electric circuit. But the circuit itself doesn't become positive or negatively charged. It's just how fast am I able to move charges around, or how much charge am I able to put into motion. And so most of the static electric problems we look at, the amount of charge is small compared with a full coulomb. They're going to be microcoulombs or nanocoulombs or picocoulombs. Okay, so here it is one more time, I guess. Here is the force formula we introduced, and here is the force constant. Now what the textbooks do, what our textbook does, is they start off with this formula, which I think is really the sensible formula to use, because from here we can make all these analogies with gravity. And so rather than just learning one force, we can kind of compare two of the fundamental forces of nature. You know, when we look at the fundamental forces of nature, it's for the most part, it's gravity, electric and magnetic forces, and then we've got a couple of nuclear forces that we'll see in those nuclear physics chapters. And then when we get to particle physics, we'll see there's kind of a fifth force out there called the Higgs force. In any case, this is the formula. The textbook switches over and uses historically what has come to be used most often, and you guys need to be familiar with both of these approaches. Instead of writing the electric force this way with a simple force constant, it's often done with something called 1 over 4 pi epsilon naught, which is called the permittivity of free space. Don't worry about what that is. If you guys have questions, we can talk more about it. But this constant is 8.85, 10 to the minus 12. Now we don't need both of these, and so what happens is the textbook starts using this one and then shifts over and mostly uses this one. I'm going to stick with this one. If you stick with this force constant, what we're going to find is that we can consistently use it all the way through the next 15 chapters, I think, is what we've got for electric forces, magnetic forces, DC and AC circuits. We can do everything in terms of the original force constant that we defined. From time to time we'll come back and see how the formulas look if we use this alternate approach instead. Okay. All right. Let's look at some values for electric charge. And the best place to start from, I would suggest, is the electron and the proton. What is the charge on an electron or a proton? And maybe, I'm guessing you guys probably are already familiar with this idea that, oh, the electron and proton have equal amounts of electric charge, but opposite sign. Okay, and as best we can measure, you know, and these measurements have been done really carefully, yeah, that's what we find. So we find that the charge on a proton, I'm going to start with the proton because that's the one that's positively charged, is 1.602 something, 10 to the minus 19 coulombs. So you can see that a proton is a tiny, really tiny fraction of a coulomb. And it turns out that the electron has the very same value of the charge, except we use a minus sign to keep track of, well, the pluses and minuses, we're really just keeping track of those so we can tell when the forces will be attractive and when they'll be repulsive. Once we've drawn the diagrams and shown where the forces are attractive and where they're repulsive, the plus and minus signs have done their job. And we can kind of drop them from our calculations. We'll see examples of that. So electric charges, they say that they're quantized in units of the electron charge, and that's what it comes down to. If I have an object and it's got a certain charge on it, it's because it either has extra electrons or it's missing some of its electrons, and that means that the charge on any object I look at is going to be some integer number multiplied by this. If I have 5 million extra electrons on the object will be negative, and it will have a charge of 5 million times the charge of an electron. So we can always refer back to, well, how many extra electrons or protons is that charge the equivalent of? Now here, we talked about this already, there's two different proportionality constants. I'm going to stick with little k. The book is going to shift over and start using epsilon naught. It's called the permittivity of free space. This traces back in the mid-1800s when electric forces and magnetic forces formulas were being developed for those. It was thought that space was filled with something called the ether. You may have heard about this in different science classes or whatever. And that the ether had mechanical properties to it. If you think back to chapter 12, like with the elastic modulus and the bulk modulus and shear modulus, it was thought that space was filled with an ether and that the ether had mechanical, physical, elastic properties to it. And epsilon naught then was thought of, what is the rate at which electric and magnetic effects can be transmitted through this ether. Turns out the ether idea has been dropped, but we still have these constants. We have this permittivity of free space. So don't worry about, don't worry about this, but I'm going to say you have to just remember that historically that's what happened, because if you move on to future classes where you're actually using some of these formulas, it's going to get referred to, it could be referred to either way. More and more textbooks that I'm looking at are sticking with just K all the way through, but the epsilon naught stuff is going to show up if you do anything with electric and magnetic forces. Okay, so you got to be prepared for either approach. All right. Let's see, how are we doing with time? We're actually doing pretty well here. So let me go ahead and look at another example. Which of these, okay, this is phrased a little funny too. It says here we have two objects. One object has a charge of Q1. What's Q stand for? Electric charge. So the electric charge on object 1 is 50 microcoulombs. So everywhere I see a micro, that is 10 to the minus 6. I got to get used to that, otherwise I'm going to be off by a factor of a million. Charge number 2 has a charge of 1 microcoulomb. Oh, that's just like the example we talked about. This one has 50 times more electric charge than object 2. So, and then they're using L, but we said this is R. And once again, they've drawn the picture incorrectly. I have to say I didn't pick up on this. The arrow should point right to the center. It's got to point to the center of the objects. Those are the distances we want to be measuring. So I guess I should go back and change those. Okay, so what it's saying is, who experiences the larger force? And that's kind of funny here, because they're saying Q1 exerts a force on Q2, and Q2 exerts a force on Q1. I guess that's, that's one way of thinking of it. The other way of saying those words is that Q2 experiences a force due to the presence of Q1. Okay, and I think that's going to be more the way I say it. So I'm going to say, is object 2 experiencing a force, and object 2 does experience a force due to the presence of charge number 1, of Q1. Q1 also experiences a force. It's experiencing a force due to the presence of charge 2 and due to its own charge. So it kind of takes both, right? I want something that's inclusive, that says you need both charges present in order for both charges to be experiencing the force. And then they're saying who experiences the larger force, and we already talked about this, so you guys are familiar. It's the same amount of force. So in my diagrams, here's object 1, here's object 2. I'll label object 1 with charge Q1, and I'll label object 2 with charge Q2, and the charge on object 1 is 50 microcoulombs. The charge on object 2 is 1 microcoulomb. And the center to center distance is 20 centimeters. Now I know the 20 centimeters has got to get converted into meters, right? And so here is the formula. F is equal to force constant times the charge 1 times charge 2 divided by distance, center to center distance squared. Here's my diagram, and notice in the diagram, because these charges are both given to us as being positive charges, I've already written in my directions. So the force directions, the directions of the force vectors, I can write in the diagram, done. Directional information is in the diagram. All that's left is to find out how many newtons is this force, and this is going to be the very same value. So these values of F that I've drawn in my diagram, I'm going to get that by multiplying KQ1, Q2 over R squared. Notice I have, at this point, I've dropped the vector signs. I don't need the vector signs anymore. All of the directional information is in the diagram. And I'm just left to calculate the magnitude. So I put all the numbers in, 8.99, 10 to the 9th. I put all the units in. I'm putting in the units here. This one was 50 microcoulombs. Now what I'm going to end up with is, there's a 10 to the 9 here. There's 10 to the minus 6 and 10 to the minus 6 because, hey, those were microcoulombs. And again, I don't want to miss 10 to the minus 6 because that's like a factor of 1,000,000. And then the units for the distance, I need to get those converted into meters. So the meters squared from here will cancel the meters squared from there, from the force constant. And the coulombs in Q1 and Q2 are going to cancel the coulombs also in the force constant. So the meters cancel out, the coulombs cancel out, what's left are newtons. And so I run the numbers in my calculator. The units are going to be newtons, and the number I came up with here, I hope that's right. I always check all these numbers. I ended up with 11.2. Now, F, what I'm writing is the force value, that's the magnitude of the force vectors. The two vectors are pointing in opposite directions, but their magnitudes are the same. And so once I've got this calculated, and I show this diagram, all the information is contained in those. All right, and again, a reminder, little r is distance. Okay. Questions on any of that? That's a good conceptual example just to talk yourself through as to how electric forces work. Okay, we're going to move on, and I think we have time to look at one more example, and then we'll take a break. We now have 3 objects. Now, I try to remind myself I shouldn't just think of these as charges because they're objects, and I don't want people thinking of me just in terms of one property. I'm so much more than just one property. So these objects happen to have an electric charge. So objects 1, 2, and 3. This object 1 has a charge of Q1, object 2 has a charge of Q2, and object 3 has a charge of Q3. Now I'm going to pay close attention to which of these are positive and which are negative. And in most problems they'll be really clear about that. If they're not clear, I might have to go back and read the problem again, but in this example they just laid it right out there. This one's negative, this one's positive, this one's negative. Now what I can do is to find out, okay, there's a couple questions that could come up here. What would happen if someone said, ask you a question, and said, what's the force, what are the forces acting on these objects? We would have to ask what that question means. So what we can do is we can step back and say, well, wait a minute, I have to think of one object at a time. So I can't think of what's the force acting on all 3 objects simultaneously. What I have to do is isolate one object. And if you think back, that's what we did back in chapter 6 when we were looking at gravitational forces, for example. So what I'm going to do is, in the question, they actually say, what is the electric force? They're calling it the electrostatic force now. Anyway, so I'm going to just call it the electric force acting on object 3. So this is object 3, and so I'm specifically asking what forces are acting on this one. Now, if we use the vocabulary or the phrasing that I was using earlier, what I'm going to tell myself is, okay, object 3 is going to experience a force due to the presence of object 1, or charge 1. So at this point, I guess I'll drop back to charges. Charge 3 will experience a force due to the presence of charge 1. Object 3 also will experience a force due to the presence of charge 2. So that means that there are 2 forces I have to calculate here if I'm going to understand all of the forces acting on object 3. So I've drawn a force they've drawn a force diagram for us. Now, these 3 charges are all lined up. So I don't have to think in terms of components. Everything is just lined up right along the what we're calling the x-axis. And so what that says is, well, object 1 is negative, object 3 is negative. Object 1, due to the presence of object 1, object 3 will experience a force in this direction. That force is going to be repulsive. So that's going to be in what we're labeling as a positive x direction. Now, of course, as we've talked about throughout Physics 3a, there's no intrinsic coordinate system built into nature. We're the ones that use coordinate systems when they're useful. And so in the coordinate system we've set up, this would be in the positive x direction. What about due to the presence of charge 2? What effect will that have on charge 3? Now this is positive. And so charge 3 is going to get pulled in the direction of charge 2. So that's going to be oppositely oriented. So object 3 is going to have 2 forces acting on it. One due to the presence of charge 1, one due to the presence of charge 2. And they're going to end up being in opposite directions because of, well, this is a positive charge and this is a negative charge, and because of where they're located. So based on location and whether or not they're positive or negative, that's determining the directions of these 2 forces. Okay, and that's how this works. So this is an extra step. We didn't have that step in gravity because we didn't have positive and negative masses. All the masses were positive, all the forces were attractive. But now we've got to stop and think about direction. All right, so here's the diagram, objects 1, 2, and 3, and labeling them in terms of the charge that they have. And then distances. So the distance between objects 1 and 3 is 50 centimeters, and the distance between objects 2 and 3 is 20 centimeters. Here is that diagram that we had outlined. And so on this diagram, what I want to point out is, again, I've dropped the vector signs. I don't need the vector signs anymore because I've determined that F13 is in this direction, the positive x direction, and force 2,3 is in the negative x direction. So once I've got the diagram drawn, what's left to do is calculate the magnitude of those 2 forces. Now I'm going to get the force on 1, 3. Notice that I'm just working in terms of magnitudes now. I've also dropped the plus and minus signs on my charges because we said the pluses and minuses are really just important in determining which direction these forces will be in. Are they attractive or repulsive? Which direction is that going to be? Once I've got the diagram drawn, I know that once I calculate the magnitude of F13 and how much force there is in F23, once I calculate those magnitudes, I'll take F13 and subtract off F23, and that'll give me the net value. So I've done that here. I'm treating all the charges now as just in terms of their magnitude. I'm writing this as 8 microcoulombs, 4 microcoulombs. Let's see, this one was -8, right? And then +3 and negative, because I dropped the signs. So I'm just going to think in terms of how much charge, how much charge is for, and then divide through by the distance where I've converted that into meters. So you can see there's a number of things to keep track of here as we go through. For this force, I got 1.15 newtons. For force 2, 3, same calculation, except I had to change the distances and I had to change the amount of charge. So I'm plugging into the same formula for each of the forces, and what I ended up with was this force worked out to be 1.15 newtons in this direction. This force worked out to be 2.70 newtons in that direction. The net force then is 1.55 newtons over there to the left in the negative x direction. Okay. Okay, that's probably a good place to take a break. So let's take a break for 10 minutes or so, and then we'll come back and look at some more examples. So you can see we're looking at things that are pretty similar to maybe what we've done